Hey, it's Patrick from Databytez, and thank you for joining me again. Today we are covering distributions, another technical theme video on data, and again, distributions characterize data sets. And you're going to see why distributions are so important. So moving on to the next slide here. You can't just do things with data. You must understand it first. And the first step to understanding a data set is uncovering its distribution. Distributions are best uncovered visually. And when you understand distributions, you can leverage a distribution's characteristics. And we're going to kind of get into that a little bit more. But first, we need to understand distributions come in two flavors: discrete or continuous. Discrete distributions have a finite sample space, meaning you can list all the possibilities on a table. It fits on a table reasonably. That's the best way you can envision it. So think about when you roll a dice. You can put out all that's either going to get 1, you're either going to get 2, you're going to get 3, you're going to get 4, and you can make what's called a frequency table, which again just highlights all the possibilities, the outcomes and the possibilities of getting those outcomes. You can also think of a deck of cards. These are finite possibilities. You can only pull one ace of spades, right, for each suite. You can only pull one king of hearts. On the other hand are continuous distributions, meaning you have a infinite sample space, meaning again you cannot list them on a table as a result, right? Instead, you must use a graph. So when you think about continuous distributions, something could be along heights. Height is an example, because you can keep splitting down height depending on your level of measurement. You can go from feet, you can then go to inches, you can go to centimeters, or you can keep breaking things down until you get even to the atomic level, like how many atoms high is someone. So really the height is a continuous space. And the other kind of thing about that's continuous in nature is it also depends what kind of height are you measuring. Height of trees, height of people. There's been many people around. How do you know how the distribution has moved over time? It kind of gets a little bit abstract in thinking. Otherwise, with a discrete distribution, you can really easily picture like a dice or a deck of cards. Continuous kind of ends up becoming a bit more abstract as you think about it. So the fundamental distributions between these two categories, these two houses that you'll normally encounter are in the discrete side, the uniform, the Bernoulli, the binomial, and the Poisson, which is very French sounding. And on the continuous, you have the normal, otherwise known as the Gaussian, the student's T, the chi-squared, exponential, and logistic. Now, there are more distributions out there, but these are kind of your bread and butter that you're going to see. And the discrete ones are pretty intuitive in nature, because you can imagine uniform just means everything has an equal possibility of happening. So again, going back to our 6-sided die, if you can visualize that, there's an equal chance of rolling a 1 as there is rolling a 2 or 3 or 4 or 5 or 6. A Bernoulli is a single trial event where you have either a positive outcome or a negative outcome, pass or fail. A binomial is just multiple Bernoullis put together, and you just have multiple outcomes of pass or fail, pass or fail. Poisson has to do with the possibility of things through time. If you were to think about how likely is a moth able to flap its wings within 3 seconds, assuming it can flap its wings 10 times per minute, or something, I don't know, something like that. It has to do with the possibility of things occurring in time giving a fixed rate. That's really where Poisson shines. And again, you won't really deal with Poisson, at least I've never had to really deal with Poisson in my years in the professional world. Perhaps in your particular study you will. And even then, uniform and Bernoulli kind of just make a lot of sense, right? Either everything is equal opportunity or it's pass or fail, and there's a different potentiality for what is passed or failed. Now, continuous. Really, the only two that matter are the Gaussian and the student's t for most things. And you'll understand why as we go a little bit deeper into it. And really, at the end of the day, it's all about the Gaussian, the normal. And that is because normal is natural. Normal is natural. The normal distribution is probably the most important and the most common distribution there is, because most things we look at are just natural phenomena in the world. Most things that we want to study. And the most important thing is you can convert these other distributions through mathematical principles, aka the central limit theorem. Now, we won't cover that here and how that works. The central limit theorem states that the distributions of the sample means follow a normal distribution, which sounds like a bunch of gobbledygook right now, but it's very powerful in the sense that no matter what you have, you can make something normal. And by making something normal, you can then leverage the properties that take place of a normal distribution. And what are those properties? Now, this really needs to have a very deeper dive in of itself. I believe so. But this info right here, this graphic, really helps get a sense for it. So the properties of a normal distribution, that you've probably seen this curve before, is that there's symmetry, that you can tell it's equal on both sides. All the measures of central tendency are equal, and there will be a video dedicated to the importance of the measures of central tendency in a later time. So stay tuned for that. It is bell-shaped, and it is asymptotic. It's an interesting word to say, but what that means to say is that the tails get really close. You see at the end where the little 2.35% is on each side, they get really close to the axis without ever touching the axis. It is defined, the normal distribution is defined by the mean and the standard deviation. In this case, we're signifying it as mu and lowercase sigma. And it follows the empirical rule, aka 68, 95, 99.97. And that really makes sense here as we look at the visual. So moving one standard deviation from the mean, from mu, at the center of this where the symmetry takes place, you cover 68% of the distribution. At 2 standard deviations away, which is why you have mu minus 2 sigma and mu plus 2 sigma, you get 95% of the distribution captured. And at 3 deviations, you get 99.7%. This is always true. It's just a fun little property of the normal distribution. And so when you get something that's normal, you can assume that once you get the mean and standard deviation, you can start doing some calculations. Things like confidence intervals. You can do z-tests. You can start seeing is something outside, has the distribution moved based on a sample. And of course, we'll get into that more in detail. But the most important takeaway is, like, all of this comes about, all of your ability to know these things, to do these things, comes from being able to understand your data set's distribution, whatever you're trying to analyze. And we discussed that the best way to do this is through visuals, kind of like how it makes things become more grounded in the understanding the normal distribution here. And also another fun thing to note, we see here that the probability space, since it can no longer be a chart, it is a curved line. But how do we do this? How do we uncover a data set's thing visually? Like, it's one thing to say that, but how do we actually do that? What tools do we use? Because we are not doing this by hand. We are never going to do any of this by hand. Well, that's where Excel comes in. And thankfully, we have a nice little Excel ready right here. So here I have a spreadsheet with a randomly generated number of yields, and you can see that this sequence of yields goes up to 10,000. So we have 10,000 sequences, 10,000 yields. Now when you look at this, you would have no idea on what it's supposed to be, right? if I were to ask you what kind of distribution does this fall under, it makes no sense. You would be like, I don't know, something. You could assume natural just because if it's something in the natural world, it's something we can observe, it most likely is normal. And you would be right, but not for the right reasons. See here, we can now determine what is this. It's starting to look a little familiar, right? This looks a lot like this. Now, what visual did I use? It is the histogram. The histogram, when you have a numerical set of data here, it goes a long way in being able to discover what the distribution of that data set is. So, how would I make this in Excel? I don't. If you must know, because I'm a little hesitant to unveil these secrets because of the fact that visuals are more complex than they may seem. And maybe it'll become apparent when I generate one out of nowhere. So let us, to create this quick visual here that from scratch, we would just highlight this range, go to recommended charts, and you can see, let's take this kind of closer up there to the one I have already pre-prepared. Looks a little bit different. You can see that these are bins. These are characteristics of the histogram. When you have a bracket, that range is inclusive. That value is inclusive within the range. When you have a parentheses, it is not. A bit more detail than you probably need. But what's important is that you can see that you can generate this using technology, using Excel. You can use Google Sheets as well. But once we uncover this, we can start calculating more fascinating dimensions, things like standard deviation. Now, that's going to be another discussion. So stay tuned for that as we start looking into measures of central tendency and also measures of dispersion, which is where the mean and standard deviation is. So remember, whenever you get some piece of data that you're told to analyze, you get it at work, you get it, you want to look at it yourself, the question is what kind of distribution are you looking at? Are you looking at normal? Are you looking at a uniform? If it was uniform, I'm wondering, what would that look like, right? Instead of looking at a curve, you would see a perfect square. You would see not a square. Well, yeah, it is. Rectangles are squares. You would see a rectangle because all possibilities are likely. All yields would be equally apparent. If you saw a binomial distribution, you would only see two bars, either one on the left and one on the right, because it would either or. It would be one or the other. So those are the kinds of things you think. Those are the kinds of things you would see, and most often than not, where you're going to come across is the normal. And if not, you can make it a normal. So stay tuned. We're going to be covering measures of central tendency next, and why they are important, what they are, how you use them. Hope you have a great one. This is Patrick from Databytez. Bye bye.